What's up? I'm Vin, and today I want to go through parts 2, 3, and 4 of the August 2022 Algebra 1 Regents. So let's get started. Question 25, we're graphing this function here, and we could just use a calculator. Now, if you could do this in your head, then great, but we get a calculator, so why not use one? So here we want to graph absolute value of x plus 1. So we're going to press math, we're going to go to the right here to number, and then ABS, option 1, is going to give us the absolute value, and we're typing in x plus 1 like this. So now that we've got this typed in, what we could do is we could press graph just to get a sense of what this looks like. And I'm going to press zoom 6 just in case our picture's out of whack. Now, if you just do your best to try to make this picture, you're going to get partial credit, but you want to be precise for the full credit. And the table, if you press second graph, is what's going to allow you to be precise. And what I like to do is I like to look at a few points before and after the vertex. Now, the table of values does not count towards our 2 points, but it does help us stay accurate. So now what I'm going to do is I'm going to plot all of these points. So now that we've got everything graphed here, we have our graph of f of x. We've got our 2 out of 2 points. Question 26, we have a table of values for the value of a car over time, and we want to determine whether a linear or exponential function is more appropriate for modeling this data, and we have to explain our choice, which means we have to write a sentence. So for a linear function, what I look for is a constant rate of change. And for an exponential function, I'll write that over here, we have a non-constant rate of change. Okay, so that's what we have to be able to determine from the table here. Do we have a constant or a non-constant rate of change? Well, notice the t values here for this column for time is going up by 5. So that part is counting by the same amount. But when we look at the y values here in the second column, this, if I do a bad approximation, is roughly a decrease of 10,000. Okay, even though technically this is decreasing by like 9,500-ish, but this is going to get the message across. When I look at the next decrease from 10,500 to 5,500, we're decreasing by roughly 5,000. So that tells us right away that we have a non-constant rate of change, because if we had a constant rate of change, the value of the car would be dropping by roughly the same amount each time, but it's dropping by smaller and smaller amounts. So that's going to tell us that we're going with an exponential function. For question 27, we want to know if the product of radical 8 and radical 98 is rational or irrational. Well, first up, you have to know that a product means multiply. So if we actually did square root of 8, and then we press the right arrow, and we multiply by the square root of 98, we could just use the calculator here, and this is going to tell us the product is equal to 28. So right away, I know that this product is going to work out to 28. So that would make our answer rational. So, and I'll just make that a little bit neater. So we're just going to not hide the entire word here. But if you wanted to show more work, what you could do is you could break down, let's say I break this down in red. Radical 8 is the same thing as radical 4 times radical 2. And radical 98 is equal to radical 2 times radical 49. And the reason why I chose these particular factors is because I want perfect square factors. So this would be 2 times radical 2. And then I'm going to be multiplying by the square root of 2, and then multiplying by 7 at the end. And now notice this part. Radical 2 times radical 2 is equal to 2. So in the next line I have 2, and then this 2 just follows, times 2. And then we have our times 7 at the end. And then 2 times 2 is 4, times 7 is going to give us 28. So here we just have to say whether it's rational or irrational, but here we could just say that our answer is rational. Okay, we don't actually have to say why. We don't have to say that this is the quotient of two integers, 28 over 1. We just have to justify our answer, which means we have to show work, which we did to determine that this is actually rational. Question 28, we have the ages of the last 16 presidents on their first inauguration day shown in this table. We want to determine the interquartile range for this data. Now for this, you have to know that interquartile range is going to be Q3 minus Q1, but the rest is calculator work. So we're going to press stat here, and we're going to edit our table. And we had 2 sets of data from before, but let's go ahead and clear these out. We go up to L2, we press clear and enter, and that'll clear out this list. And then we go over to L1, we press clear and enter, and now I'm just going to enter in all 16 values. Now once we've got this all typed in, we're going to press stat, and we're going to calculate, and this is single variable statistic because we just have one column of data, and this is going to tell us all the stuff we need to know. If we scroll down here, we have all this useful information. We have our minimum value, our first quartile, median, Q3, and our max value. So once again, if we want to find our interquartile range, what we're going to do is we're going to take this information here, we're going to do 61.5 minus, we have 51, and this is going to work out to 10.5. If you want to be really thorough here, what you could do is you could translate these values over here. You could say your min value is 43. You could actually label Q1 is equal to 51. Your median is 54.5. So it doesn't hurt to write a little bit extra for questions like this, just in case the rubrics change year to year and the expectations change, because once you write all this, it's obvious where you're getting Q3 and Q1 from your table from the calculator. Question 29 is worded a little bit strange here, but we have the cost of 1 pound of grapes is. So anytime I hear the word is in math, I think equal. So I'm going to have G is 15 cents more means 15 plus the price of 1 pound of apples A. So I have 15 plus A like this. Okay, so that's our first equation for G. And then next what we have is the cost of 1 pound of bananas is, so that's B equals twice as much as 1 pound of grapes. So that's 2 times G. And now for the actual question, write an equation that represents the cost of 1 pound of bananas, so that's B equals, in terms of the cost of 1 pound of apples. So then what we need to do here is we need to use this system of equations by substitution idea. We have B equals 2 times, and G is equal to 15 plus A. So us just doing this answers the question. What we have is the price of 1 pound of bananas in terms of the price of 1 pound of apples. Okay, so notice there's just a coefficient of 1 here. So this will answer question 29. Now for question 30, if you know your transformation rules and you want to describe how you get from f of x to g of x, notice f of x is the start. So this is where we're starting. And we're going to land here at g of x. And if you know your transformations, you could see the inside is being increased by 2. And when you replace the x with whatever you have there with a plus 2, it shifts the graph 2 units to the left. But let's say you forget all that stuff. What you could always do is you could go to the calculator and you could type in both functions. So we could type in first x plus 1 squared, because that's going to be the starting function in red. So you have x plus 1 squared, and if we graph at the same time x plus 3 squared, we could just actually look to see how does the graph actually transform. So this is useful if you forget rules, use the calculator to investigate. And if we press graph here, notice the first graph in blue, the vertex is at -1, 0, but the red graph is the same parabola just shifted 2 units to the left. The vertex moves to -3, 0. So our answer definitely checks out. Now question 31, we could try factoring this, but this is not going to factor nicely. We're going to actually have to use the quadratic formula. We're going to have irrational roots. So just know you could always use this quadratic formula here no matter what your quadratic equation is. So some students actually prefer to use this one all the time because it always works. And then what you have to be able to do with this quadratic equation is identify the a value, which is the coefficient of x squared, which is in this case 3. Our b value is -5. Make sure you take the minus with it, and the c value is -7. So now we just plug into this formula. We have x equals -5 plus or minus, we have the square root of -5 squared. And I would absolutely write parentheses, because if you write this in the calculator, you're going to get -25, which is not going to match parentheses -5 squared. So just be on the lookout for that. That's a very common trap. So we have this minus 4 times a times c, and this is all over 2 times a, so we have 2 times 3 like this. So now when we want to write out our two solutions, we have x equals our first answer and x equals our second answer. We just have to type this into the calculator. So we go back to the main screen here. We're going to press alpha y equals enter, and this is going to pull up a fraction to make things neater. Now we have -5, which is just 5. And first I'm going to find the plus. We have to do plus then minus. But first we have 5 plus the square root is second x squared. And now in parentheses what we have is we have -5 squared. So let's pretend we don't want to risk doing any mental math here, because you do get a calculator, so why risk doing the mental math? I mean, unless it's 1 plus 1, you know, it doesn't hurt to type this in. So you have -4 times 3 times -7, and then all divided by 2 times a, and a was equal to 3. So here, look, if you want to just write 6, you can, but let's pretend we forgot 2 times 3 is equal to 6. So now we just press enter, and we have our first solution is going to be to the nearest tenth, 2.6. But now, just to save time, when you want to do this all over again, but this time, and I pressed enter too many times, let me just do this once more. This time we're going to have 5 minus the square root, because notice here it's -5 plus or minus. So now I could type this all over again with the minus, or I could just go up to that plus sign and type minus, and it's going to do this for us. So our two solutions are going to be 2.6 and negative 0.9. So once again, we have x equals 2.6 and x equals negative 0.9. These are the two solutions to this question here. Question 32, we are factoring completely. And just know, anytime I have to factor something completely, I always look for a GCF first. Look for a greatest common factor first, because this will always make the question easier. So here I notice I could take out a common factor of 3. So this I could say 3 times, and if we divide each thing by 3, we're going to have y squared minus 12y divided by 3 is 4 times y. And then we have minus, if we do 288 divided by 3, I could use a calculator for this, or just say 28 divided by 3 is 9 with a small remainder of 1, and then 3 goes into 18 6 times. So this is how this is going to factor. And now the next thing, if you could do this in your head, then great, is you take 96 at the end. And I know it's negative 96, but we'll do that plus minus stuff in our heads. And we could break this down a few different ways. So this would be 2 times 48. We could also say this is divisible by 3, and this would be 3 times 32. And then if we try 4 next, 4 would go in 24 times. And then if we move down the list here, not 5, 5 is not going to work. 6 would work. 6 times, let's see, this goes in 16 times like this. And then the next one, which is going to be the one we need, is 8 times 12. Okay, and the reason why I know it's going to be these two in some form is because they are 4 units apart. Since we're multiplying to negative 96, the next thing I would think about here, if I'm doing this all in my head, is that I would have to determine which one of these is going to be negative. And since they're adding up to a negative, the bigger number has to be negative. So I'm thinking negative 12 and 8. If you add those, you get negative 4. And when you multiply those, you get negative 96. So now this is going to factor. We're going to have 3 times, that stays in front. We have y minus 12 times y plus 8 like this. So this is our expression factored completely. So question 33, we have Thomas taking a 140-mile bus trip to visit his grandparents, and the trip is outlined on the graph. Explain what might have happened in the interval between D and E. So notice here, the total trip is 140 miles. So by the time Thomas gets to point F, that's when he's basically at his destination. So what's going on between D and E? Well, notice here, the y-axis represents how many miles are covered, and the x-axis is covering how many hours it takes. So notice here that in this space here, this is the 110-mile mark, that for the length of this distance here, this is between 2 and 3, this would be 2.5, that from 2.5 to 3 hours, the bus is not moving at all. So we have to think about this. What could have happened here? We could say that the bus stopped at a rest stop so that it could get gas, or maybe people could use the bathroom and get some food. Okay, this explanation just implies that the bus is not moving between points D and E. And now we want to state next on which interval does the bus travel fastest. So that means when is the average rate of change in miles per hour the greatest? So when is the slope the steepest? Well, it's obviously not going to be from B to C and from D to E, because on these intervals, the bus is not moving. Now, if you look on this first interval here, the rise over run, this is at the 0.5 mark, is that the bus, if we label this here as, let's say, the point 0.520, and this is the point 00, the bus is traveling at a rate of, we're going up 20 over 0.5 miles per hour. So on that interval here, if we simplify that, 20 divided by 0.5 would be 40. So the bus is traveling at an average speed of 40 miles per hour. Now on the next interval here, what you could do is you could count the rise over run, or you could just find the slope. So notice at point D, this is the point when we're at 2.5, comma 110. And at point C, we're at the point 1, comma 20. So if we find the slope between these 2 points, and remember the slope formula is y2 minus y1 over x2 minus x1, you could find the slope with the formula, or you could count the rise over run. So let's say you want to use the formula. So on this interval, what we would have here is the rate of change would be 110 minus 20. So we're taking the difference of the y values, and now we divide by the difference of the x values like this. So this would work out to 90 divided by 1.5 miles per hour. And if you just punch this in a calculator, 90 divided by 1.5 is equal to 60. So the bus is traveling at an average speed of 60 miles per hour from C to D. And now on the last interval here, you could see that this one is the least steep, or it's less steep than the one before it. And if we find the slope between these 2 points, let's say here, if we do it this way, we're going to the point, this is 3, 110, and point F is at 4, 140. So if we find the slope here, the slope on this interval would be 140 minus 110 divided by 4 minus 3. And this is going to be in miles per hour, but we would have 30 divided by 1, which is 30 miles per hour. So for this specific situation here, the interval in which the bus is traveling fastest is the interval from C to D. Now, we already did the work for this, but how many miles per hour was the bus traveling during this interval? We calculated this over here. The bus was traveling 60 miles per hour on this specific interval. Now, the last thing we need to find is the average rate of speed in miles per hour for Thomas's entire trip. So that would mean going from point A to point F. We're going to find the slope between those 2 points. So notice at F, we're at the point 4, 140, and at A, we're at 0, 0. So we would just do 140 minus 0 divided by, this x value is 4 minus 0, and this is miles per hour. And if we work this out, 140 we're doing divided by 4 miles per hour. And if you just type that in a calculator, you're going to get 35 miles per hour. So that's our solution to the last part. So the first thing we'll do is graph these. So first we'll press y equals, and we're going to have x squared. So we have this minus 4x, and then we're going to tack on a plus 3. And then in the next line, we have 1/2 x, and that we could just write as 0.5. You could write 1 divided by 2, but I'll write 0.5x and then plus 1. And I'm going to press zoom 6 here just to clean up the picture a bit. So we can see that we have 2 points of intersection, but if we want to be really precise, we press second graph, and we're going to need these table of values here to find ourselves a solution. So we'll color code these here. I'll graph f of x here in purple, and that's going to be the one in blue here from this table, because you can see the rate of change is not constant for a quadratic, but it is for a linear function. So the first point we could probably plot here is -1, 8. So we go over here 1, and then we're going to go up 8 units like this. And then next we would have 0, 3 bringing us here. So we're going to be at this point, and then we'd be at the point 1, 0, and then 2, -1. And then we're going to have 3, 0, and then we have 4, 3. So this is going to have symmetry now because our vertex is going to be at 2, -1. And then the last point we'll look at here is at 5, 8. So now I'm just going to connect these as best as I can. But that's why it can't hurt to write your table of values next to your solution. So that way, if your drawing is a little spotty, the person grading it knows like what you were intending to draw. So just pretend you're as bad of an artist as I am. So now this is the graph of f of x. So I'm just going to label it here in purple. Now the next one is the graph of g of x, which we'll graph in red. So here, if I go a little bit in the negative, let's say I'm here at the point -2, 0. So I'm at the point -2, 0. And then next I'd be at -1, 0.5, but that's kind of annoying to draw, so I'm just going to stick with the whole number. So we have 0, 1 next. That's going to bring us here. And then after 0, 1, the next whole number I'll have is 2, 2. So I'm going over 2, up 2. And then for the next one here, the next whole number, I have 4, 3. And notice this is the one that matches. See, this is the one I would prefer to write as my solution because it's a nice whole number coordinate to look at here. So this one here that I'm drawing in red is... I'm sorry, the one that I'll just label here in a different color. This is the point of intersection here at 4, 3. So this is our common solution. We also have one at x equals 1/2, but notice that the table doesn't have something showing up here for x equals 1/2. We'd have to plug into both, and that's a little bit of extra work. So this is the nice solution. So now we'll just write our solution out. We have a value of x equals 4 that satisfies f of x equals g of x, and that's because the graphs intersect at x equals 4. Now, if you're a little worried, what you could do is you could plug x equals 4 back into the original function for f and g, just to show you that they both get a y value of 3. But you could even look here in the table, see at x equals 4, their y values match. So for question 35, we have a store sells grapes for $1.99 a pound, strawberries for $2.50 a pound, and pineapples are $2.99 each, and Jonathan has $25 to buy fruit. And now we're given the amounts. He plans to buy 2 more pounds of strawberries than grapes. He also plans to buy 2 pineapples. So this is all important stuff here, but now we're given x represents the number of pounds of grapes. And we need to write an inequality in one variable that models this scenario. Okay, well, what we need to know here is that the amount of money that he spends on grapes is $1.99 per pound. So since he's buying X pounds, if we multiply $1.99 by X, that's going to tell us how much Jonathan spends on grapes. Plus, he's also buying strawberries, $2.50 per pound. But now we have to think, how many pounds of strawberries is Jonathan buying? He's buying 2 more pounds of strawberries than he is grapes. So if he's buying X pounds of grapes, then he's buying X plus 2 pounds of strawberries, because that's 2 more than X plus 2. And then he also plans to buy 2 pineapples. So that's plus 2 times the price of a pineapple is $2.99. So you have 2 times this. And now for this part, this is where it gets a little bit tricky. But we need to set up an inequality to relate it to how much money he has. But just think about it. If you're buying a whole bunch of stuff, your bill has to be less than or equal to the amount of money you have in your pocket. If the bill, which is on the left, is greater than what you have in your pocket, then you can't afford what you're about to buy and you have to put some stuff back. So the total bill has to be less than or equal to 25. And this will model the scenario. So now we're going to do a little algebra to determine the maximum number of whole pounds. So we're rounding to the nearest whole number, the number of whole pounds of grapes that Jonathan can buy. So here what I would do is I would just write this down. We have $1.99 times X plus, and now we're going to distribute. We have 2.5 times X, so that's 2.5X. And then we have plus 2.50 times 2 is going to give us 5. And then next we have 2 times 2.99. And this we could use a calculator, or I just think 2 times 3 is 6. So then I just shave off 1 cent twice, and that's going to give us 5.98. Okay, so that's just a little bit of math we have to do to get this started. And now what we could do is we could combine like terms. So what we have up next is we have $1.99 times X plus $2.50 times X. But we'll leave the symbols out with the money till the end. And if I'm doing this in my head, I'm going to do 250 plus 2 is 450, and then I just lose a cent. So that's going to be 4.49 times X. Plus, if I do 5 plus 5.98, that's 10.98. And this is less than or equal to 25. So now we just subtract. We're going to subtract 10.98 on both sides. And on the right side of the inequality here, these terms are going to cancel. So we're going to have 4.49x is less than or equal to, and when we subtract those two values, we're going to have 14.02 left. So now the last thing to do to solve for x is going to be to divide by 4.49. So that's going to give us this here, this expression. And now this we just type into a calculator, and that's going to tell us x is less than or equal to, and if we do this divided by this, we'll have 3.12249. But now we just have to make sure we answer this question. Determine algebraically the maximum number of whole pounds of grapes he could buy. So here, Jonathan can buy 3 pounds of grapes, and we'll abbreviate pounds with LBs like this. Question 36, we have to graph this system of linear inequalities on the graph below, and then we have to determine if negative 50 is in the solution set. So for questions like this, the first order of business, or what I think about, is getting these in the form of mx plus b. And just know in general, when you have something in the form of mx plus b in slope-intercept form here, what you have is you could identify the slope, which tells you the rise over the run of the line, and then the b value is your y-intercept, and in a way that tells you where the line begins. So what I would do for the first inequality is I would subtract 3x on both sides, and if we write that over here, y plus 3x is less than 5, we're going to go minus 3x on both sides, and that's going to give us y is less than negative 3x plus 5. And the reason we do this is so that it's in the form of mx plus b. And now the second one here, if I show this work on the side, we have 1 is greater than or equal to 2x minus y. So for this one, I would add y to both sides. That way the y is on the left. And then from here, we have y plus 1 is greater than or equal to 2x. So if I do minus 1 on both sides, that's going to tell us that y is greater than or equal to 2x minus 1. So that essentially transforms both of these and makes it easier to graph. So I rewrote both inequalities over here so that now we could just go ahead and graph these. And what I think of first when I'm looking at the first inequality in blue is when I analyze this, we have y is less than negative 3x plus 5. The slope of negative 3 jumps out at me. And if I write it as negative 3 over 1, that's going to tell us to go rise negative 3, which means go down 3, and we're going to run 1 unit. So we're going down 3 to the right 1. And this tells us our y-intercept. And in a way, the y-intercept tells you where to begin. So I'm going to start on the y-axis at 5. So I'm going up 1, 2, 3, 4, 5. And I'm starting here, but now I'm going to go down 3 units to the right 1 unit. And I'm just going to keep repeating this. I'm going down 3 units to the right 1 unit. That way, I'm keeping up with this slope of -3. So I'll just do this a few more times here. But one thing I have to be mindful of is that if I do want to go backwards, I'm going to go up 3 to the left 1. And I know that I'm doing this right if my points stay on a straight line. But one thing we have to be very, very, very careful of is that this is just less than. So when I connect these points, I'm not making a solid line. I'm going to be making a dotted line like this. Okay, so just connecting these points with a dotted line like this. And I'll go ahead and throw on my arrows here. And we're going less than. So that means I'm going to be shading under the line like this. So I'm just going to go ahead and shade everything under this line. And that's just highlighting the solution to the first inequality. But now for the second inequality, our thought process has to change a little bit. So for the second inequality, when we're thinking about y is greater than or equal to 2x minus 1, now we have a slope of +2. And if I call it 2 over 1, this is telling us to rise 2 and to run 1 unit to get from one point to the next. And our y-intercept here is -1. So this time I'm starting at -1. And to get to the next points, I'm going up 2 to the right 1 unit. So I'm going to keep doing this. And notice my points are forming a straight line. And that's, if in case you count wrong, let's say you wind up over here, you know that something's up because there's no longer a straight line. So that's just how I keep track as I'm doing these. And if I want to go backwards, I'm going to go down 2 to the left 1. And I know I'm going correct, once again, if I'm keeping that straight line. But now since this is greater than or equal to, this one I'm going to connect with a solid line like this. Okay, so when there's an equal to sign attached to your inequality, then you have to make the line solid. And for this, we are considering y is greater than or equal to, so I'm going to be shading above this line. So this is going to highlight our solution set here. You could see our solution set is going to be in this space here. And I'm going to go ahead and label our solution set with an S. So now for the last part, we want to determine if -5, 0 is in the solution set. So let's look. We go to the left 1, 2, 3, 4, 5, and we're going up 0. And this we could say, yes, -5, 0 is in the solution set because it lies in the intersection of the shaded regions. Now, two things I would do before moving on. I would label both of these inequalities. And originally, this one here was 1 is greater than or equal to 2x minus y. And the second inequality here, originally, before we simplified it, was y plus 3x is less than 5. Okay, so I labeled both of these, but then the next thing I would do is check by plugging into the original inequalities. So this little check here, I'll just go ahead and do this in the corner, is I'm going to plug in the point x equals, so we're going to plug in x equals -5 and y equals 0. And if I plug into, let's say, the blue one, what I would have here is I would have y equals 0 plus 3 times x is -5, and that's less than 5. And if we simplify this, we're going to get -15 is less than 5, and that is definitely true. Now, if I want to check with the second inequality, I have 1 is greater than or equal to 2 times x is -5, and then we have minus y, and minus y is equal to 0. And this would give us 1 is greater than or equal to 2 times -5 is -10. That is also a true statement. So this checks out with both inequalities. So I'm confident in this answer. So now for the final boss, we're in part 4, and let's answer the 6 credit question. So for this question here, we have ice cream, and there are small and large sundaes. And on one day, 30 small sundaes and 50 large sundaes were sold for $420. And then on another day, we had 15 small sundaes, 35 large sundaes, and those sold for $270, and sales tax is included in all of this. That just means life is going to be a little bit easier. We don't have to do any percents. And now what we have here is if x is the cost of a small sundae and y is the cost of a large sundae, we need to write a system of equations to model this situation. So to model this situation, x represents the cost of a small sundae. Since 30 small sundaes were sold, if we do 30 times x, that'll tell us how much money was made with small sundaes. Plus, the large sundaes, 50 of them were sold. So that's 50 times y, and the total amount of money made for those on that day was $420. So this is our first equation. Now, our next equation, we have 15 small sundaes. So that's 15x plus, and then 35 larges, that's 35 times y, is equal to 270. So for the second part of this, we have Peyton thinks that the small sundaes cost $2.75 and the large sundaes cost $6.75. Is Peyton correct? Justify your answer. Now I'm going to take an educated guess and say Peyton's wrong, because then we wouldn't have much to do for the last part. So let's go ahead and plug in. So let's use the calculator to check if Peyton's right. So if Peyton was correct, then 30 times we have $2.75 for a small. So 30 times x, but x is 275, plus, and then we have 50 times the cost of a large sundae according to Peyton is $6.75. So we're going to do 6.75. And will this add up to 420? Yes, but you have to be very careful. In order for this to work, it also has to check with the second equation. So then we have to do 15 times 275 plus, and now we're going to use 35. So let's type this correctly, 35 times 675. And when we work this one out, this time around we get 277.5, which is not equal to 270. So Peyton is not correct, because when we plug into the second equation, we get a value not equal to 270. So now let's record this result. We have 15 times 275, or 2.75, plus then we have 35 times 6.75, and this was equal to 277.50. But now let's make the statement here. This is not equal to 270, so we could say Peyton is not correct. Okay, for this one, we don't have to write a because it just says justify your answer, which means we need mathematical evidence to say why Peyton is not correct. Okay, but this answers the second part of this question. For the last part of this question here, we want to determine algebraically what is the value of x and y, the cost of one small sundae and one large sundae. So for this one here, what we're going to do is we're going to write this down, and we're going to be strategic here and think about which variable is easier to eliminate. So now for the last part of this question, we're going to determine algebraically the cost of one small sundae and one large sundae. So for this, we basically just have to solve for x and y. Now there's a few ways we could do this, but this one I would want to do by elimination. So here I think it's going to be easier to eliminate x, because if we multiply the bottom equation by -2, notice we're going to have 30x and minus 30x, and those will cancel nicely. So what we're going to have next, we're going to have 30x plus 50y equals 420. And then when we multiply the bottom equation by -2, we're going to have -30x minus 70y, and then -2 times 270 is going to give us -540. So now what we could do is we could add these equations together. These terms are going to eliminate. 50 plus -70 is -20, and we just tack on the y, and this is going to equal -120. So now divide both sides by -20, and that's going to give us y equals 6. So now to solve for the other variable, we're going to plug back in. So now it doesn't matter which one we plug into. Let's say we plug into the first one. So I'd have 30x plus 50 times y we just found is equal to 6, and this is equal to 420. So this is going to give us 30x plus 300 is equal to 420. Now I would subtract 300 on both sides, and that's going to bring us to this step. We're going to have 30x is equal to 120. And now just divide both sides by 30, and this is going to give us x equals 4. So now if we want to write out our answer formally, determine the cost of one small sundae. So we could say the cost of a small sundae is $4, because that was the value of x. But now we'll just turn it into money, and the large we just found is equal to $6. So here is our solution to the system of equations. Now, if time permits, I would take our solution to the system and plug it back into the original. And notice this time when we plug in x equals 4 and y equals 6, this one checks out for both equations. So I am 100% that our answer is correct.